नमस्कार। मैं आनंद कुमार खत्री, एसोसिएट प्रोफेसर ऑफ जूलॉजी, गवर्नमेंट डूंगर कॉलेज बीकानेर। आज के हमारे लेक्चर का विषय है हाइड्रोस्फीयर। जैसा कि हमने पूर्व में हाइड्रोस्फीयर से संबंधित बात की है, जिसमें हमने वाटर साइकिल और प्रेसिपिटेशन से रिलेटेड बात की थी पिछले चैप्टर के अंदर। इसी से रिलेटेड आगे ग्राउंड वाटर एंड river runoff. The term R in the water balance equation S is equal to P minus E minus R. इस इक्वेशन के अंदर टर्म R for change of soil moisture storage represents groundwater and river runoff losses from the soil moisture zone. Water percolates from the soil moisture zone through the unsaturated zone to the water table. Flow through the unsaturated zone is complicated. After a rainfall, water may form a nearly continuous phases in pores in this zone, but with drying, the last amount of water is held in cluster of at points of contact of solid grains and as thin films as on solid surface. The flow paths of water become more tortuous and the water conducting properties decreases rapidly. Structured solids, soils and fractured rock in the vadose zone may act as conduit for fluid to reach the water table. Because of the complex geometry of water contained in the unsaturated zone, the properties of water are expressed by means of empirical relationship. Darcy's law, derived in 1856 from experimentation by the French engineer Henry Darcy, permits quantification of water flow through porous media. The law states that the rate of flow Q of a fluid through a porous layer of medium, it may be sand bed, is directly proportional to the area A of the layer and to the difference delta H between the fluid heads at the inlet and outlet faces of the layer and is inversely proportional to the thickness L of the layer. And the analytical expressed equation Q is equal to K A delta H upon L, where K is a constant characteristics of the medium. The term K for a porous rock medium is the volume of fluid of unit viscosity passing through a unit cross sections of the rock in unit time under the action of a unit pressure gradient. This characteristic is called permeability. The permeability of a rock is dependent on the geometric property of the rock, such as porosity, shape, and size, distribution of constitute rock grains, and degree of cementation of the rock. Permeability of rock vary greatly. Unconsolidated sands may have permeabilities measured in hundreds of darkes, whereas consolidated sands that will transmit reasonable amount of fluid have permeabilities of 0.01 to 1 Darcy. A rough idea of the meaning of 1 Darcy of permeability, which equals 9.869 into 10 to the power square meter, can be obtained by imagining a cube of sand 1 foot on a side. If the sand has a permeability of 1 Darcy, approximately 1 barrel of water per day will pass through the 1 foot cube with a 1 pound pressure head. The general equation of Darcy can be modified to express flow in both the unsaturated zone and the saturated groundwater zone. Groundwater is constantly in motion. When a lake or stream intersects the groundwater table, the groundwater communicates directly with these bodies of water. If the groundwater table is higher than the stream or lake level, a pressure head will develop such that the groundwater flows into the water body. Conversely, if the groundwater table is lower than the river or lake level, then the pressure gradient induces flow into the groundwater. Most groundwater ultimately reaches the channels of surface streams and river and flows to the sea. On the average, groundwater contributes to total river runoff about 30% of its water on a global basis. Water runoff from the land surface is that part of the precipitations which eventually appears in perennial or intermittent surface streams. Streams flow generation mechanisms have been studied for several decades, and there is now considerable knowledge regarding rainfall runoff processes and their controls. This understanding is the result of both careful observation from field experiments and the heuristic simulation of hypothetical realities with rigorous mathematical models. The discharge measured at the downstream end of a channel reach is supplied by channel flow inflow at the upstream end of the reach and by the lateral inflows that enters the channel from the hill slope along the reach. The lateral inflow may arrive at the streams in one of three forms: the groundwater flow, second, subsurface storm flow, third, overland flow. Groundwater flow provides the base flow component of stream that sustain their flow between storms. The flashy response of stream flow or to individual precipitation events may be ascribed to either subsurface storms flow or overland flow. Under intense rainfall event during which the surface soil layer becomes saturated to some depth, water is able to migrate through preferred pathway rapidly enough to deliver contribution to the stream during the peak runoff period. The conditions for subsurface storm flow are quite restrictive. The mechanism is most likely to be operative on steep, humid, forested hill slopes with very permeable surface soil. Overland flow is generated at a point on the hill slope only after surface ponding take place. Ponding cannot occur until the surface soil layer becomes saturated. It is now widely recognized that surface saturation can occur because of two quite distinct mechanisms, specifically Horton overland flow. It is named for American hydraulic engineer and hydrologist Robert E. Horton. And the second one is the dune overland flow, which is named for British hydrologist Thomas Dune. The former classic mechanism is for a precipitation rate that exceeds the saturated hydraulic conductivity of the surface soil. A moisture content versus depth profile during such a rainfall event will show moisture contents that increase at the surface as a function of time. At some time, at some point in some point in time, the surface becomes saturated and an inverted zone of saturation begins to propagate downward into the soil. It is at this time that the infiltration rate drops below the rainfall rate and overland flow is generated. The time is called the ponding time. The necessary condition for the generation of overland flow by the Horton mechanism are a rainfall rate greater than the saturated hydraulic conductivity of the soil and a rainfall duration longer than the required ponding time for a given initial moisture profile. Horton overland flow is generated from partial areas of this hill slope where surface hydraulic conductivities are lowest. In dune overland flow, the precipitation rate is less than the saturated hydraulic activity and the initial water table is shallow or there is a shallow impending layer. Surface saturation occurs because of a rising water table, ponding and overland flow over at a time when no further soil moisture storage is available. The dune mechanism is more common to near channel areas. Dune overland flow is generated from partial areas of the hill slopes where water tables are shallowest. Both Horton and dune mechanism results in variable source area that expand and contract through wet and dry periods. Total river discharge and the chemistry of the discharge vary from continent to continent. Some continents are wetter and some drier than the world average. But the deviations are not extreme. The runoff per unit area from Asia and Europe is almost exactly equal to the water overage. It is a little lower in Africa and North America, and it is considerably higher in South America. Antarctica is frozen and Australia is arid, and so they contribute little runoff. Also, since their areas are relatively small, they do not affect the global runoff average significantly. The water draining the continents have quite different chemistries. Those from Europe are very rich in calcium and bicarbonates, whereas those from Africa and South America are not. North American and Asian rivers are somewhat intermediate in their concentrations of these dissolved constituents. Such differences in composition reflects a variety of factors including runoff, temperature and relief. But certainly the bulk composition of the continental rocks is in contact with these water and their underground surface play a major role. The surface rock of Europe are rich in carbonate and those of South America are not. The latter are dominated by sediments rich in silicate minerals. The chemistry of groundwater and river runoff is being modified by human activities on a global scale. The natural dissolved riverine input of major constituents to the ocean already has been increased by more than 10% because of human activities. In the case of sodium, chlorine, and sulfate, the increases are as high as 30%. In the United States alone, total water use is equivalent to one third of total runoff, and with about 2% of the total water coming from underground wells. In the southwestern region of the country, water supplies have been tapped heavily and in some areas have been exhausted with no hope of replacement. This extensive use of fresh waters in the United States and throughout the globe makes them particularly susceptible to pollution. Leachates from fertilizers, herbicides, and pesticides are found in some freshwater bodies. Toxins or excessive amount of certain inorganic or organic chemicals are present. Radioactive elements have been detected, and some surface water bodies have had their salinities increased dramatically, rendering them useless for human consumption. It is therefore imperative that countries closely monitor the use of freshwater system and promote their conservation. Thanks.